In this problem, I'm going to be optimizing something to do with a box that we're manufacturing. And what it says here, we've got 2,700 square centimeters of material available to make a box with a square base and an open top. That means there's not a top to the box, so no material is used for the top. We want to find the largest possible volume of the box. Now, we're given square centimeters of material. Square centimeters, that's a measure of area. And so this is the material making the box. It's the area, essentially, of all the sides of the box that we're concerned with. Often we think of that then as surface area. So in an optimization problem, there's usually a goal. The goal here is to get the largest possible volume. I'm trying to maximize the volume. The volume then is the quantity I'm trying to maximize. I could call that Q. So I'm going to want an expression for the volume of this box. To do that, I'm going to have to relate together different features of the box. I'm probably going to have to draw a picture of this box. And so it's going to be a square base. It's not necessarily a cube. So my box might look something like that. I've got these sort of hidden sides of the box there. And since it has a square base, that means that these four sides along the bottom all have to be the same length. I can just use one variable for that. I can call those four sides all x. Now, the height of the box here, that's another length. That's not necessarily related to x here. So I could call that another variable y. And what we have to look at here then, we're trying to maximize the volume, find the largest possible volume. I'm trying to maximize here my volume, I can call Q. Well, this shape is called a prism. It's essentially has a square base, and if we do cross sections, if we cut across this shape going all the way up from the base, every cross section is going to be identical. That's called a prism. And the volume of a prism is always the area of the base times the height. So the area of the base is x squared, the height is y. So my function I'm trying to maximize will be x squared times y. The only problem with that is to maximize a function, I want to take the derivative and find any critical numbers. There are two variables here, so I can't take that derivative. I need to try to eliminate one of these variables using something else in the problem. So I need to find a way of relating x and y together other than the volume. And that's where this 2700 is going to come in. So I know that from that I'm going to have, I don't have a top, right? No top, but I am going to have a bottom. And the bottom, let me just draw it a little better there. The bottom is a square, right? All four sides of the bottom are x. So the area of the bottom is just going to be x squared. For the sides, well, we have four sides. Each side is sort of long and narrow here. It's going to be x along the bottom and y along this length. Just like this rectangle right here on the side of this box, it's x along the bottom and its height is y. That gets repeated for all four sides as I go along the box, right? There's going to be four of those. So when I look at that, the area of the sides, each side is xy, but there's four of them. So the total area of the sides will be 4xy. I don't have to worry about the top here. And I know that the total of that material has to be 2,700 square centimeters. So if I take x squared plus 4xy, that has to equal 2,700. Now I'm just going to solve this for one of the variables. Since it's just y to the first power, it's going to be easier solving for y than trying to solve for x. So I'm going to try to get y by itself. So I'm going to subtract x squared. And then divide by 4. By 4x. Yeah. So y will be 2,700 minus x squared all over 4x. And now I can go back to my function q. Q is going to be x squared times y, but y is 2700 minus x squared all over 4x. This is really x squared over 1. So one of these x's is going to cross out one of these x's. So that's going to leave an x in the top. I'm going to distribute that x to both terms in the numerator. And so I'm going to get my function q is going to be 2700x minus x cubed all over 4. I can just divide the numerator, both parts of the numerator, by 4. So I'm going to get q 2700 divided by 4 is 675x minus 1/4 x squared. And that's essentially the setup to the problem. So we look back at what I'm trying to do. I'm trying to maximize this function q, but now I've rewritten q this way. So I want to maximize q, which is 675x minus 1/4 x squared. To maximize a function, I need to find any critical numbers, so that means I have to look at q prime. The derivative of 675x will just be 675. Oh, I made a mistake back here. All right, so, oops, that's okay. This back here, this was x cubed, and I wrote x squared. So this is 1/4 x cubed. All right. So up here, same sort of thing. That's going to be 1/4 x cubed. So when I take the derivative, now the 3 comes down. 3 times 1/4 will be 3/4. And we subtract 1 from the exponent, so we get 675 minus 3/4 x squared. And I want to set that equal to 0. That's how I find critical numbers. Or I look for where it's undefined. But since this is just a nice polynomial function, there are no denominators, it can't be undefined. So I set it equal to 0. I'll add 3/4 x squared to both sides. And then to get x squared by itself, I'll multiply both sides by 4/3. And so that leaves me with just x squared. 675 divided by 3 will be 225 times 4. So that's 900. And then when I take the square root, so it would be plus or minus 30 for x, but x is a length of the side of this box, so the negative answer really doesn't make sense in this applied problem. So my only critical number I'm going to get is x equals 30. That will allow me then to figure out what y is. I go back here. Y is this 2700 minus x squared over 4x. So 2700 minus x squared over 4x. Right, I'm just going back to this expression here, and I'm just replacing x with 30, right? So that's going to be 2700, 30 squared is 900. So that's going to be 1800 over 120. Let's see, so that, divide top and bottom by 10. And that goes in there. When I divide that, I get 15. So y is going to be 15. And so what we need to do then is just verify that this is actually the largest possible volume of the box. To do that, I need to sort of do a first derivative test here. If it's the largest possible volume, then if it's a maximum, I'm expecting that I would have something like this, where 30 would be there at the peak. What I need to do is take a couple values on either side of this, like 29 and 31, and see what happens if I put those x values into my derivative up here. Okay, so I'm going to look at q prime of q prime of 29. That would be 675 minus 3/4 times 29 squared. Well, here's the deal. If I plugged in 30, that gave me 0. So if I plug 30 in, 30 times 30 squared times 3/4, that exactly zeroes out. If I plug in 29, 29 squared is going to be a little bit less than 30 squared. That means this whole thing is going to be a little bit smaller. That means when I take this subtraction, it's going to end up being positive. You can, of course, do this on a calculator. I just don't feel like it. So that will be positive, so it will be increasing. However, if I do q prime of 31, now 31 squared is a little bit bigger than 30 squared. So this is going to end up being a little bit bigger than 675, so that's going to be a negative number. But again, you can check it on a calculator if you don't believe me. So I had an increasing function and then a decreasing function. That means 30 is actually the maximum. So the maximum occurs when we had x equals 30 and y equals 15, but we have to pay attention to what the problem is saying. Is find the largest possible volume of the box, right? So I need the volume here, not what x and y are. So my volume, that's equal to this value q, which is x squared times y. So that's going to be 30 squared times 15. That's going to be 900 times 15. And if we do that, we get 1350. And of course, it was 30 feet, 30 centimeters, 15 centimeters. So this would be cubic centimeters.